Hello everyone, welcome back. Oh, I'm glad this shirt showed up. I didn't check that. We wore a yellow shirt Friday, put that in front of the green screen, and we were semi-translucent. This blue one's working out. All right, when we left off, we were talking recursion. We were doing this one, or I gave you this one as homework. Given an array of events, compute recursively if the array contains somewhere a value followed in the array by a value times 10. What? If the array contains somewhere a value followed in the array by that value times 10. Let's look at this example. What we're looking for is this value, and then we notice that the one next to it is 2 times 10. Right? We see this value, and the one next to it is 3 times 10. So let's try to do this. We see that we have a couple of parameters here. We have the array that's getting passed around from recursive call to recursive call. We have this index, and it's how we kind of track our current position. Think of this as I. Keep in mind that recursion is an alternative for iteration, and so all this is the integer I. We're going to be updating that as we go. That's how we traverse the array. Ultimately, we need to return a Boolean. So let's get started here. I'm going to keep going through the array, updating this index. Eventually, it's going to be out of bounds. So I want to make sure this is a base case for us. If index is greater than or equal to the length of our array, we're out of bounds. I want to check this first before I check anything else in my method to make sure that we're in bounds for the rest of the method. If we are out of bounds, that means we never found something that meets this scenario. So we're going to return false. If I'm still here, what it means is index is in bounds, and I can check this. I want to know if the current element is equal to 10 times the one next to it. Okay. If you look at these, we are starting at the beginning and working our way towards the end. So what I want to do is check the element, the current element, and then the one that follows it. If the element at this current index is equal to the one next to it is equal to nums at index plus 1 times 10. Now, kind of an important note about precedent here. This multiplication should be done first before we actually check for equivalency. Simply put, your PEMDAS has a higher precedence than your relational operators. So we're asking, is the current element equivalent to the one next to it times 10? Sorry, I put this on the wrong side. We want to know, are those two things equal? Right? Is the current element times 10 equal to the one next to it? Is 2 times 10 equal to 20? Is 3 times 10 equal to 30? That's what we're looking for. If this is true, we have found it. We're going to return true. If I'm still here, that means we're in bounds. We've already checked. This is false. We need to basically keep going. So we're going to have our recursive call where we call the method passing in the current array, and we're going to update our index so that we kind of traverse through the array. So subsequent calls, the index will be increased by 1. We'll keep doing that, and eventually we either find this scenario or we go out of bounds. Let's try this. Ooh, we got to think about this. What's happening here? Right? I'm getting some array index out of bounds, but I thought I was checking that, right? Here I'm trying to make sure that I'm still in bounds. Well, if I take a look at this case, let me kind of zoom this out. Here they gave me an array with only one element. Okay. If I have only one element and I try to check the one next to it, I'm out of bounds. So what we're getting is 0 gets passed in initially. We would ask, is 0 greater than or equal to the length of our array? It's not. So we need to basically check to see, is the current element times 10? The current element is 3 times 10. That gives me 30. Okay, is 30 equal to the element after it? Well, there is no element after it. So this is where the index out of bounds is occurring. And what I am seeing is a suggestion of we should do nums.length minus 1. Right? We only basically want to do this if there are at least 2 elements. And that's what that will kind of help us out with. Hey, Marius. This is the only thing that actually gets me up in the morning. Okay, so back to our slides. Whenever we left off, we wrote linear search, but we did so using recursion. Now, we wrote that in a class called Searcher. My whole intention was that we would come back and do binary search, because binary search is a pretty popular one to kind of write recursively. Oh my gosh, I almost blend in with the, let's fix that, with the literal slides. All right, so I'm going to recap binary search. This is actually in the CSA curriculum, although of course this year's kind of botched. But that being said, we could just use the refresher. I mean, binary search is just cool anyway. So binary search works by continuously breaking the array into halves and checking the midpoint until a key is found. A precondition exists that the array must already be sorted. So this is an alternative to linear search, as we've talked about before. It is faster than linear search, but the array has to be sorted. And that sounds like a big deal. It seems kind of goofy. Like, what am I going to do? Take my array, run it through a sorting algorithm, which, keep in mind, the fastest sorting algorithms that we learned were like merge sort, which is an n log n algorithm. Then you perform binary search. Why not just do linear search to begin with? But kind of what I told you last year, what we do in practice is actually just keep the array sorted. Whenever you go to add an element to the array, the data structure, you put it where it's supposed to go to begin with. And what that means is that at any given moment, your array is just already sorted. And so at any given moment, you can perform binary search. Ultimately, what gets used in practice is something called a binary search tree. So if you're really interested in this concept, check that out. Let's perform binary search. Ooh. Let me turn off my webcam here for this, because I am covering it up with my big old head. I am gone, but I am still here. Let's do binary search 6. First thing we're going to do is find the midpoint. I'm giving you a beginning and end index, right? So we need to find the midpoint based on that. This is kind of obviously the midpoint at this index right here. So we're going to ask the question, is the key 6, right? We're searching for 6. Is it less than, greater than, or equal to the element at my midpoint? Because 6 is less than 14, I'm going to narrow my search down. Now, our original slide said that binary search works by continuously breaking the array into halves and checking the midpoint until the key is found. The thing is, breaking an array in half is a very taxing type of operation. What we actually do in practice, instead of making the array actually smaller and smaller and smaller, is that we use these little indices, to kind of mark the beginning and end of our search area. So I'm going to find my midpoint. Because 6 is less than the element at that midpoint, I'm going to lower my search not by breaking the array down in half, but by bringing end down. We're going to lower the search area. End is going to flip to the other side of mid. Mid would disappear. And now this is my search area between beginning and end. I'm just ignoring this part over here. We don't actually physically want to make a new array that is smaller and transfer elements over. I just want to narrow my search range. Let's find the midpoint. Now, note that there are 2 possible midpoints in this. We could pick over here on the left side. We could pick over here on the right side. Your algorithm could choose either. It doesn't matter. But in practice, once you write it, it's going to kind of favor the left side or the right side. And because of truncation, these things tend to favor the left side. So that's what we're actually going to do here. We're going to favor the left side, making this our midpoint. We're going to ask, is the key that we're searching for 6 less than, greater than, or equal to? Because it is greater than, we're going to narrow our search range. The way we do that in this case is bring beginning up, or beg up. It's going to flip to the other side of mid. Mid would go away, and then we would want to find our midpoint. Again, we have 2 possible midpoints. But as we stated earlier, once our algorithm kind of chooses a left or right, we will always favor that. So we'll favor the left. Because we favored the left last time, we'll favor the left this time. So this is my midpoint. Now we're ready to ask our question. Is the key that we're searching for 6 less than, greater than, or equal to the element at this point? It's equal to. So we found it. What we would return is the index, indicating that we have found it. Now, that's great, but what if the key isn't in the array? That is, most importantly, how do you know when to stop? Let's kind of visually demonstrate that by looking for an element 25, which clearly isn't in my array. I got the exact same array. We got the exact same beginning and end points. First thing we do, find the midpoint. We would then ask, is 25 less than, greater than, or equal to? Because it is greater than, we're going to lower our search range by bringing bag up. It'll flip to the other side of mid. Mid would go away. And now we're ready to find our midpoint again. Again, our algorithm is likely favoring the left side, so that's what we're going to choose. We will then ask, is 25 less than, greater than, or equal to the element at this midpoint? Because it is greater than, we need to lower our search range by bringing the beginning up. It'll flip to the other side of mid. Our midpoint would go away. We then find our midpoint. It's right here. We would ask, is our key 25 less than, greater than, or equal to? Because it is less than, we're going to bring end down. End is going to flip to the other side of mid. And this is where our algorithm would stop. Notice that end is on the wrong side of bag, and that is the moment where I know that the element that I'm searching for, the key, is not actually in my array. Sweet. We're going to write a method, binarySearch, that returns the index to which the specified int occurs, and the specified int array -1 if it does not occur. Again, small p. Let's bring back the webcam. This is binarySearch to me. That this indicates the way that we talk about binarySearch, like, oh, you use this to find if an element's inside of an array. That sounds like it's a contains method to me, and it should return a boolean. This is really an index of, but the way we're going about it is where you're doing binarySearch. So let's open up IntelliJ. Ooh, let's go. I'm gonna open recent, flip back to my searcher that we're working on Friday. Our index of, this was linear search. I'm gonna come in here and let's add binarySearch. Doesn't really matter where it goes as long as it's in the body of the class. We got public static int binarySearch, which is going to take in an integer array, call that R, and a key that we're searching for. Now, this is going to be a lot like the linear search that we did on Friday, where there's actually a lot of data here. Like, I need these index markers. In the case of binarySearch, I need my beginning and end index markers. If we're not going to modify the array, right, this thing is not actually going to be cut in half. The way that we're going to narrow our search range is using these index markers to keep track of the section that I'm searching through. So I'm going to ultimately need more parameters here to pass in. Just like with the linear search, however, I'm going to probably have this starter method that kind of kicks everything off. Of course, we're going to be searching the whole thing. So the initial call probably shouldn't have all of the data. We'll come back to that. So binarySearch, I've got the key, I've got the array that I'm searching through, the key that I'm searching for. I'm going to need bag to keep track of where I should start my search, and end, bag and end to kind of define my search area, I should say. Let's return the index at which key occurs in R -1 if key does not occur. This uses binarySearch in order to do that. So a precondition here precondition. R is sorted in ascending order. Oh, I know there's typo. Change to ascending. Thank you. Thank you. Precondition. Our array is sorted, and we're ultimately trying to figure out where key occurs. Now, there's a lot of integers here. I'm using an integer array to demonstrate this concept. Let's bring this up some. Using an integer array to demonstrate this concept. So each individual element, what we'll be looking for is an integer. Now, these indices, beg and end, they have to be integers. But this concept could, in theory, work for something like strings or doubles, at which point you would change what you're searching through and what you're searching for. Sweet. Okay. How do we know when to stop? What's our base case look like? Length is equal to 1. Yeah, you got to keep in mind, we're not actually breaking the array down to be smaller. What we're doing is changing beg and end to make sure that we're in, to kind of lower our search range. So here is effectively a base case. Or another way you can think about it is, I'm going to perform the actions as long as beg is less than end. Right? So I'm kind of writing this in reverse in terms of the base case. Right? If beg is less than end, then we're okay to perform our binary search. Otherwise, I'm going to return a -1, indicating that it is not there. So this, despite being written in reverse, is kind of our base case. If beg is less than or equal to end, I'm okay. This means that we can still find our midpoint. That is the first thing we actually want to do. We'll create integer mid. And kind of as we saw from our slides, the midpoint is in relation to beg and end. One common mistake that people start out with is they look at the initial values of beg and end and they try to base it on maybe the length of the array, right? Using an index of 0 or using the length to figure out the initial midpoint. But the thing is, beg and end are going to kind of update over the life of this. And so our midpoint needs to be in relation to beg and end. We will take, what is it? It's end plus beg divided by 2. I think you can also just subtract. Right, let's take a look at this example. So here, my value for beg is 0. My value for end is 8, I believe. 8. So we have 8 minus 0. Right? 8 minus 0 gives us 8. Divided by 2 gives us 4. 0, 1, 2, 3, 4. That's this initial midpoint. Okay, what if my stuff is here? Well, I've got beg, which still has a value of 0. End, which is a value of 3. We would do 0 plus 3. That would give us 3. Right? 3 minus 0, which gives us a value of 3. 3 divided by 2. This is 1.5, but it's going to truncate to 1. And so that's what I mean by we're going to favor the left-hand side. Right? This index is 1. We had the option of favoring either, but because of the truncation, we're going to favor the left-hand side. Maybe it should be beg plus end. And then it show up in my test cases. I think you're right, Carson. That just flat out makes sense to me. Let's roll with that. It may matter. So we'll find our midpoint. We'll play with this. We'll find our midpoint. Now we need to ask the question, is the element at that midpoint, or is the key, the thing that we're looking for, less than, greater than, or equal to? Okay. If it's equal, we found it. We could just stop there. So this is like a base case within my base case. If key is equal to the current element, that is ARR at mid, then we found it. We can stop here. We can return the current index. The current index being mid. Okay. However, if the thing that I'm looking for is like greater than or less than, I need to do some updates here. Now, what we're doing is, in this case, right, what we're looking for, 6, is greater than 3, so I need to bring bag up. I need bag to be mid plus 1. But I don't want to just change it in my current method call. I need to basically do this process over again, but with new values for end and bag, in theory. Technically only a new value for bag, because that's the only one I'm updating in the actual example. So let's ask the question. If the key that I'm looking for is actually greater than my current element, what I need to do is update bag. But the way I'm going to do that is put a recursive call stack, or recursive call onto the stack. We're going to call binarySearch again, looking through the same array, looking for the same key, but now bag has been updated. Bag, instead of it being what it was, is going to be mid plus 1. Right? Bag is going to be mid plus 1. Notice that end is not changing. Sweet. Otherwise, so there's a third scenario here. We've checked for equals. We've checked for greater than. If we hit this, it's effectively the less than scenario. So maybe a comment that you like that is unnecessary is key is less than the element at mid. Well, if key is less than element at mid, let's jump back here. Right, we found the midpoint. We found the midpoint. We're going to ask, are these equal? Is the element that I'm looking for, 6, equal to the array at mid, 14? No. Is 6 going to be greater than 14? No. We would hit this return statement where 6 is less than 14. That is true. In that case, I need to bring end down. It's going to flip to the other side of mid, or that is mid minus 1. So we're going to call binarySearch, passing the array as is, the key as is. In this scenario, my bag is not changing. What's changing is my end. So we'll pass in bag as it is. End, however, is going to flip to the other side of mid. It'll be mid minus 1. And that's it. Let's try it. I think this plus should work. Here I have an array that's already in order. We got 3, 7, 42 parentheses. Oh, around this addition. Y'all probably been chatting that up for like a hot second. Thank you. I'm in my main method. We have an array that's already in order. It's got a length of 6. Okay, let's look for some stuff. I'm going to perform a binarySearch, passing in nums. Let's look for 7. And I need to pass in the initial bag, which is 0, and the end, which needs to be essentially this element, or length minus 1. Okay, something kind of note, the initial end, it could actually be out here, and your algorithm would still work. It would kind of change some initial midpoint selections, but it's not actually an issue. Let's try this. I'm performing binarySearch, looking through nums for 7. I should get back a 1, because 7 does occur, and it is at index 1. Let's try some other things here. Let's look for these numbers, guys. 420. Okay, I get a 4. This is looking pretty good. Just making sure. That addition probably was the right way to go. Let's look for something that's not in the array, like 50. -1 because it is not there. Okay, Now this is kind of a mess, right? In practice, you don't want to have to type in these indices. Obviously, we're searching through the entire array initially. So what you kind of want probably is something like we did with our linear search, a little starter method, something to clean this up, to make it a little bit more practical. So what I would probably do in practice is you have this binary search that takes in all this data. It's the one that's doing all the heavy lifting, but I want something to actually get it started. I would overload this method with public static int binary search, passing in an integer array, and just simply, the key that we're looking for. So this one just exists to get things started. This is the one that I would call like from the main method or some other client class. This would be the one that I would actually use. This is the one I would actually use, while this one actually does all of the work. And all this method does is simply get things started. It'll call the main binary search method that's doing all the work, passing in these things for us. All right, so all I'm doing is calling the other binary search. I've overloaded binary search. We have the method with the same name in the same class, but the parameters are different. This one takes in an integer array and an integer, whereas this one takes in an integer array, an integer, and two more integers. So I'm calling that binary search from here, passing in basically the start and end, the initial start and end of the array. So what that allows me to do is, in context, I don't have to pass in those parameters. I get something that's a little bit cleaner. We want to perform binary search, looking through nums for this key, 50. This is calling my little starter method. I should still get a -1. Why don't we search for something else to kind of prove that this is kind of working. So our little starter method is going to get called. All it's doing is making the initial call to binary search, passing in 0 and the end of our array. Now, of note, I kind of said that you don't have to do the -1. We did in kind of our examples, largely because it just looks better. All that does is change some initial midpoint. So I'm looking for 99. The change I made is that I took off the -1 here. And what I'm showing is looking for 99. It's still not there. This is still working. Let's try to find maybe 42. Yeah, 42 occurs at index 2. This is still working. Okay. Now this could add or subtract an iteration. A recursive call. Not a big deal. But this is binary search done recursively. Kind of cool, kind of sweet. All right, let's take a look at our homework. I want you to do recursion 1, all-star. I know every single one of you now have that song stuck in your head. I apologize, sorry. I'm not that sorry. I'll see y'all tomorrow. Let's chill.